Welcome to this problem walkthrough. In today's session, we'll be tackling problem number 573, titled Squirrel Simulation. This is an exciting challenge that involves optimizing paths and efficiently collecting resources. Whether you're here to improve your problem-solving skills or to gain a deeper understanding of algorithmic thinking, you're in the right place. Let's get started. In this problem, we are tasked with helping a squirrel collect nuts in a 2D grid. The grid contains three key elements: a tree, which is where the squirrel will store the nuts once collected, the nuts themselves, scattered at specific positions, and the squirrel, starting at a given position on the grid. The squirrel can move in any of the four cardinal directions: up, down, left, or right, and each move costs 1 unit of distance. The goal of this problem is to minimize the total distance the squirrel travels while collecting all the nuts and storing them in the tree. Here's how the process works: the squirrel picks up one nut at a time, moves to the tree to store it, and then continues collecting the next nut until all nuts are stored. Our job is to determine the minimum total distance the squirrel must travel to complete this task efficiently. To solve the problem, we need to work with the following inputs: the height and width of the grid, which define its dimensions. Additionally, we are provided with the position of the tree as a list of two integers, x, y, the starting position of the squirrel is another list of two integers, x, y, and the positions of the nuts, which are given as a list of multiple x, y pairs. The output of our solution will be a single integer representing the minimum total distance the squirrel needs to travel to collect all the nuts and store them in the tree. Let's consider an example to illustrate this further. In a grid of height 5 and width 7, the tree is located at position 2, 2, the squirrel starts at 4, 4, and there are two nuts at positions 3, 0, and 2, 5. The minimum total distance traveled by the squirrel in this case is 12. Looking at the details of the first example, we can break down the calculation of the total distance. First, the squirrel moves from its starting position at 4, 4, to the first nut at 3, 0, which takes 5 units of distance. Then, the squirrel carries this nut to the tree at 2, 2, traveling another 3 units. Next, the squirrel moves back to collect the second nut at 2, 5, which costs 3 units of distance, and finally stores this nut in the tree, traveling another 3 units. When we sum up these distances, 5, 3, 3, and 3, the total comes to 12. Now, let's consider a second example. In a smaller 3x3 grid, the tree is located at 0, 0, the squirrel starts at 2, 2, and there is one nut at 2, 0. The squirrel first moves 2 units to reach the nut and then another 4 units to carry it to the tree, resulting in a total distance of 6. To further clarify, the second example shows that the squirrel travels 2 units from 2, 2 to the nut at 2, 0, and then 4 units from 2, 0 to the tree at 0, 0, giving a total of 6 units. When solving this problem, we must also consider the constraints. The grid's height and width range from 1 to 100, and the number of nuts can vary between 1 and 100. Additionally, the positions of the tree, the squirrel, and the nuts are all distinct and remain fixed throughout the process. All positions are guaranteed to be within the grid's bounds. Edge cases to watch for include scenarios with only one nut, situations where all positions are aligned in a straight line, large grids up to the maximum size of 100 by 100, and cases where the grid is densely packed with nuts. Our solution must account for all these scenarios while ensuring the total distance is minimized. To solve this problem, we first consider a brute force approach, where the squirrel simulates all possible paths to collect the nuts and store them in the tree. For each nut, we calculate the distance from the squirrel's starting position to the nut, and then from the nut to the tree. By summing these distances, we can determine the total path cost. However, this requires evaluating all possible permutations of the collection order to find the minimum cost, which quickly becomes computationally expensive. A key observation here is that the order of nut collection only matters for the first nut because, for all subsequent nuts, the travel path always involves going from the tree to the nut and back. Therefore, the main decision lies in which nut the squirrel collects first. Calculating distances for all permutations has a factorial time complexity, O(n), which makes it infeasible for larger inputs. To address this, we turn to an optimized greedy approach, which focuses on minimizing the additional distance introduced by the squirrel's first trip to a nut. For the remaining nuts, the cost is fixed at 2 times the distance between the nut and the tree. In the optimized greedy approach, the focus shifts to selecting the first nut in a way that minimizes the total distance traveled. For the first nut, the squirrel starts at its initial position, travels directly to the nut, and then proceeds to the tree. This path differs from the fixed round-trip cost of going from the tree to the nut and back. To make this decision, we calculate the gain or penalty associated with choosing each nut as the first. The gain is defined as the difference between the round-trip cost of traveling from the tree to the nut and the one-way cost of traveling from the squirrel's position to the nut. Mathematically, this gain is calculated as distance, tree, nut, distance, squirrel, nut. The nut with the maximum gain should be selected as the first nut. The steps for this approach are straightforward. First, compute the total round-trip cost as if the squirrel starts at the tree for all nuts. Then, for each nut, calculate the gain associated with collecting it first. Adjust the total cost by replacing one round-trip cost with the squirrel's first trip cost, and return the minimum total cost. This method has a time complexity of O(n), because we only iterate through the nuts once to compute gains, and the space complexity is O(1), requiring only a few variables for the calculations. Given the problem's constraints, the optimized greedy approach is the strategy of choice. It simplifies the problem by focusing solely on the first nut, while treating the rest uniformly. This reduces the computational complexity from O(n) in the brute force approach to O(n), making the solution scalable even for large inputs. While the brute force approach guarantees correctness by evaluating all permutations, it's computationally impractical due to its factorial growth. In contrast, the greedy approach is mathematically sound, leveraging gain maximization to ensure correctness while avoiding unnecessary calculations. This strategy strikes a balance between simplicity, efficiency, and accuracy. By adhering to the problem's constraints and eliminating redundant computations, the greedy approach provides an optimal blend of performance and correctness, making it the most practical solution for this problem. In this problem, we're tasked with helping a squirrel collect nuts scattered across a 2D grid and deliver them to a tree. The goal is to minimize the total distance the squirrel travels while ensuring every nut is collected and brought to the tree. To do this, we need to carefully calculate the squirrel's path. Let's begin by understanding the distance calculation logic. For each nut, the total distance the squirrel travels consists of two parts: the distance from the squirrel's starting position to the nut, and the distance from the nut to the tree. Using this, we can express the total path cost for a specific nut as the sum of these two distances. This calculation forms the basis for evaluating the efficiency of different paths and is key to solving this problem optimally. Now that we understand the distance calculation, let's explore different approaches to solve the problem. First, in a brute force simulation, we can generate all possible paths the squirrel could take to collect the nuts in different orders. For n nuts, this involves generating all permutations of the nut collection order, then calculating the total distance for each permutation. While this guarantees the optimal solution, the factorial time complexity makes it infeasible for larger inputs. Instead, we can optimize this process by analyzing how the choice of the first nut affects the total path cost. The insight here is that the first move contributes significantly to the total distance, so we calculate a value called delta for each nut. This delta represents the difference between the distance from the squirrel to the nut and the distance from the nut to the tree. By prioritizing the nut with the smallest delta, we can minimize unnecessary travel. Using this greedy approach, the squirrel always moves to the most optimal nut first, and this process is repeated iteratively until all nuts are collected. When designing an algorithm, it's important to consider edge cases. For instance, if there's only one nut, the squirrel simply collects it and delivers it to the tree directly. If multiple nuts are equidistant from the squirrel or the tree, it doesn't matter which one is chosen first, as the result will be the same. Additionally, if any nuts are already at the tree, they can be ignored, as they do not contribute to the path cost. These scenarios highlight the importance of adapting the algorithm to handle special situations effectively. Key insights from this problem include the power of greedy optimization, where we iteratively reduce the travel cost by focusing on the smallest delta for the squirrel's first move. Another valuable technique is pre-computing all pairwise distances between the squirrel, nuts, and the tree. This avoids redundant calculations and speeds up the algorithm. Efficient data structures, such as arrays to store distances and priority queues to select the next best nut, further improve the algorithm's performance. There are trade-offs to consider when comparing the brute force approach to the greedy method. Brute force, with its factorial time complexity, is guaranteed to find the optimal solution but becomes impractical for large inputs. In contrast, the greedy approach reduces the time complexity to linear with respect to the number of nuts, as it selects and updates distances iteratively. To implement this efficiently, we use specific data structures. The grid itself is represented as a list of coordinates for the squirrel's position, the nuts, and the tree. A distance matrix is pre-computed to store all pairwise distances, allowing for constant time retrieval during the algorithm. Optionally, a priority queue can be used to efficiently select the nut with the smallest delta, ensuring each iteration of the greedy algorithm is both fast and precise. These optimizations together strike a balance between accuracy and computational efficiency. Finally, let's analyze the overall complexity of the solution. Pre-computing the distances between the squirrel, nuts, and tree takes linear time with respect to the number of nuts. The greedy selection process iterates over all nuts, contributing another linear factor. This gives the algorithm a total time complexity of O(n). To optimize further, we avoid recalculating distances during each iteration by pre-computing and storing them in a matrix. For scenarios with a very large number of nuts, heuristics such as clustering the nuts and processing them in groups can help reduce the problem's scale, making it manageable. These improvements ensure the algorithm remains efficient even as the problem size grows, providing a practical solution to the squirrel simulation challenge. The provided Python implementation solves the LeetCode problem 573, squirrel simulation, by minimizing the distance the squirrel travels to collect all nuts and bring them to the tree. Here's a detailed explanation. 1. Understanding inputs and initialization. The function minDistance takes the grid dimensions, height and width, the positions of the tree and squirrel, and a list of nut positions. Variables total_distance and max_saving are initialized. Total_distance accumulates the doubled distance of all nuts to the tree, as each nut's round trip is counted. Max_saving tracks the best saving achieved by starting at a specific nut instead of the tree. 2. Iterating over each nut. For each nut, the Manhattan distance to the tree_distance, is calculated. This value represents the distance the squirrel must travel if it were to start at the tree for this nut. The total_distance is updated with twice tree_distance since the squirrel must make a round trip for each nut. 3. Calculating potential savings. The distance from the squirrel's starting position to the nut, squirrel_distance, is calculated. If the squirrel starts at this nut instead of the tree, the saving is the difference between tree_distance and squirrel_distance. The max_saving is updated to track the highest saving possible across all nuts. 4. Final calculation. After calculating the total round-trip distance for all nuts, the best saving, stored in max_saving, is subtracted. This gives the minimum distance the squirrel must travel while optimizing its starting point. 5. Return result. The minimized total distance is returned as the output. This approach ensures that the solution is efficient and handles all edge cases, such as varying positions of the tree, squirrel, and nuts. The code runs in O(n) time, where n is the number of nuts, making it scalable for larger inputs. By focusing on maximizing savings for the squirrel's initial movement, the optimal path is determined without redundant calculations. This is the Java implementation of LeetCode problem number 573, Squirrel Simulation. The logic mirrors the provided Python implementation, where we calculate the total round-trip distance to collect all nuts and maximize savings by starting at the most optimal nut location for the squirrel. Key differences include explicit type declarations for variables and the use of Java's math library for absolute value calculations. To start, we are given the input values for a single nut scenario. The grid is 5 times 5, the tree is located at position 2, 2, the squirrel begins at 4, 4, and there is one nut at 3, 3. We initialize two variables. Total_distance is set to 0, which will track the total round-trip distance for the nuts, and max_saving is set to -infinity, which will help us determine the best savings when the squirrel picks up a nut first. Now, we loop through the nuts, and since there is only one nut at 3, 3, we start by calculating its distance to the tree. Using the Manhattan distance formula, the distance from 3, 3 to the tree at 2, 2 is 2. The round-trip distance for this nut is twice that, which equals 4. We add this to total_distance, making it 4 so far. Next, we calculate the potential savings if the squirrel starts by picking up the nut at 3, 3. The squirrel's distance to this nut is also 2, using the same Manhattan distance formula. The savings in this case would be the difference between the tree distance and the squirrel distance, which is 2 minus 2, resulting in 0. We update max_saving to the maximum of its current value, -infinity, and this saving, which makes max_saving equal to 0. Finally, we compute the result by subtracting max_saving from total_distance. With a total distance of 4 and no savings, the result is 4. Thus, the output for this example is 4. Now we look at an example with multiple nuts. The grid remains 5 by 5, the tree is at 2, 2, the squirrel is at 4, 4, and there are 2 nuts at 3, 3, and 1, 1. We initialize total_distance to 0 and max_saving to -infinity. Starting with the nut at 3, 3, its distance to the tree is 2, making the round-trip distance 4. Adding this to total_distance brings it to 4. The squirrel's distance to this nut is also 2, resulting in a saving of 0. We update max_saving to the maximum of -infinity and 0, so max_saving remains 0. Next, we consider the nut at 1, 1. Its distance to the tree is also 2, so the round-trip distance is again 4. Adding the round-trip distance for the nut at 1, 1 brings total_distance up to 8. The squirrel's distance to this nut is 6, calculated using the Manhattan distance formula. The savings in this case is the tree distance of 2 minus the squirrel distance of 6, which gives -4. We update max_saving to the maximum of its current value, 0, and -4, so max_saving remains 0. Finally, we compute the result as total_distance minus max_saving. With total_distance at 8 and max_saving at 0, the result is 8. Thus, the output for this example is 8. Now, let's consider a case where the squirrel starts closer to a nut. For this example, the input remains similar, but the squirrel starts at 1, 1, which is close to one of the nuts. We initialize total_distance to 0 and max_saving to -infinity. Starting with the nut at 3, 3, its distance to the tree is 2, so the round-trip distance is 4. Adding this to total_distance makes it 4. The squirrel's distance to this nut is 4, resulting in savings of -2. We update max_saving to the maximum of -infinity and -2, so max_saving becomes -2. Now for the nut at 1, 1, its distance to the tree is 2, so the round-trip distance is again 4. Adding this to total_distance makes it 8. The squirrel's distance to this nut is 0, so the savings is 2. Updating max_saving to the maximum of -2 and 2 gives max_saving a value of 2. Finally, we calculate the result as total_distance minus max_saving. With a total_distance of 8 and max_saving of 2, the result is 6. Thus, the output in this case is 6. To analyze the time complexity of the solution, we start by considering the iteration through the list of nuts. Suppose there are n nuts, the algorithm goes through this list exactly once. For each nut, it calculates 2 Manhattan distances, one between the nut and the tree, and the other between the nut and the squirrel. Both of these distance calculations take constant time, or O1. Since these operations are performed for each of the n nuts, the total time for iterating through the list is O(n). Additionally, during this loop, the algorithm updates the total round-trip distance and evaluates the maximum saving, both of which are constant time operations. Therefore, these updates do not add any extra complexity, and the overall time complexity remains O(n), determined primarily by the iteration over the nuts list. Now, let's evaluate the space complexity of the solution. The input includes the list of n nuts, the coordinates of the tree and squirrel, and the dimensions of the grid. Since these inputs are provided and not created within the algorithm, they do not contribute to additional space usage. The algorithm itself uses only a handful of scalar variables, such as the total distance, the maximum saving, and some loop variables. These require a constant amount of space, or O1. There are no additional data structures, nor does the algorithm involve any recursive calls that would use extra stack space. As a result, the overall space complexity of the solution is O1, as it only uses a fixed amount of auxiliary memory regardless of the size of the input. Let's compare this efficient approach with a naive solution. A brute force method would involve evaluating all possible paths for the squirrel to collect the nuts and return them to the tree. This would mean considering all permutations of the nuts, which results in a factorial time complexity of O(n). However, our current solution bypasses this inefficiency by focusing only on the optimal savings for the squirrel's first trip, reducing the time complexity dramatically to O(n). Now, in terms of best, average, and worst-case scenarios, the algorithm consistently processes all the nuts, so the time complexity remains O(n), regardless of how the nuts are distributed. For example, whether all nuts are equidistant, randomly spread, or the maximum saving is achieved at the last nut, the algorithm's complexity does not change. Mathematically, this is because each nut involves a constant amount of work calculating two distances and updating variables, which is O(1). For n nuts, this work scales linearly, leading to the O(n) time complexity. Furthermore, as we've already seen, the space complexity is O(1), since the algorithm only uses scalar variables with no additional memory overhead. When approaching this problem, there are several common pitfalls to watch out for. First, failing to handle edge cases can lead to incorrect solutions. For example, consider scenarios where no nuts are available. Your program should either return 0 or manage this gracefully. Other tricky situations include the squirrel's starting position overlapping with a nut or the tree, or when all nuts are equidistant, which can lead to unnecessary computation. Additionally, skewed distributions of nuts, where most are far from the tree, can affect the efficiency of your solution. Another frequent mistake is miscalculating Manhattan distances. Ensure you're consistently applying the formula as the absolute difference in x coordinates plus the absolute difference in y coordinates. Errors like swapping axes or inconsistent subtraction can easily creep in. Inefficient iteration is another issue, especially in brute force approaches. Iterating over the same nuts multiple times without eliminating redundant paths can significantly slow your solution. Finally, overcomplicating the problem is a trap many fall into. While advanced algorithms like Dijkstra's might seem appealing, simpler heuristics are often sufficient for grid-based problems like this one. One specific aspect to focus on is optimizing for the squirrel's first nut. This choice has a major impact on the total distance traveled, so failing to prioritize it in a greedy approach can lead to suboptimal results. Now, when preparing for interviews, it's crucial to understand the problem constraints. Be clear on the grid dimensions, the number of nuts, and the positions of the squirrel and tree. These details help you decide whether to use a brute force, greedy, or more optimized solution. Greedy thinking is often beneficial in grid traversal problems, as it allows you to minimize the local cost, such as the squirrel's first trip. However, it's equally important to explain the trade-offs behind your chosen approach. For instance, you might justify why a greedy strategy is sufficient compared to a more complex algorithm. Pre-computing distances between the squirrel, nuts, and tree is another valuable optimization technique, as it avoids redundant calculations. Lastly, discussing edge cases with your interviewer demonstrates thoroughness and attentiveness to detail, which are highly valued in problem solving. This problem has strong connections to other grid-based challenges, making it a great stepping stone for related problems. The canonical version, LeetCode 573, focuses on minimizing distance in the squirrel simulation context. For practicing traversal techniques like depth-first or breadth-first search, LeetCode 200, the number of islands problem, is an excellent choice. If you want to build intuition around distance calculations, LeetCode 1266, minimum time visiting all points, provides a simpler scenario. On the other hand, LeetCode 847, shortest path visiting all nodes, delves into more advanced concepts like dynamic programming for path optimization, making it a more complex but rewarding challenge. Exploring these problems will deepen your understanding of grid-based algorithms and help you see the broader applicability of the techniques used here. There are several approaches to solving the squirrel simulation problem, each with its own trade-offs. A brute force method involves simulating all possible orders of collecting nuts and calculating the total distance for each. While this is straightforward to implement, it becomes computationally expensive as the number of nuts increases, with a time complexity of O(n). A more efficient option is the greedy approach, where you minimize the first trip's distance from the squirrel to a nut and then optimize the subsequent trips based on the total distance. This method is faster, with a time complexity of O(n), but it doesn't always guarantee the global optimum. For guaranteed optimality, dynamic programming can be used to store intermediate results for visited nodes, eliminating redundant calculations. However, this approach requires more memory and is more complex to implement. Finally, graph-based methods, such as representing the problem as a graph and applying shortest path algorithms like Dijkstra's, can be useful for more intricate variations of the problem. While these methods can handle complex constraints, they are often overkill for simpler scenarios like this one. Each approach has its place, and understanding their trade-offs will help you choose the best strategy for the given constraints. Great job making it to the end. To recap, we tackled the squirrel simulation problem, discussed its challenges, and explored a brute force approach to solving it. Remember, optimization problems are all about finding the right balance and understanding trade-offs. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more fun and engaging coding lessons. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!